we're going to talk about transmitting and action potential, finishing up our neurobiology unit. And I'm going to show you this to remind you of what we did last time as an introduction.
We've looked at the resting potential in a neuron that is not transmitting nerve signals. What happens when the cell is stimulated? A stimulus may change the permeability of the cell membrane to sodium or potassium ions. This alters the distribution of charge in the cell body, and if the change is great enough, it triggers a signal called an action potential that moves down the axon. How does the action potential move along the axon? Voltage-gated channels in the membrane open and close in response to voltage changes across the membrane. When no action potentials are being transmitted, most of these channels are closed. An action potential begins when voltage-gated sodium channels open and sodium ions rush into the cell. The plasma membrane becomes positive on the inside and negative on the outside. Very quickly, the sodium channels close, while voltage-gated potassium channels open, allowing potassium ions to rapidly diffuse out. The plasma membrane returns to being positive on the outside and negative on the inside, and the potassium channels close. Meanwhile, the sodium ions inside the cell have diffused to adjacent areas, causing a slight change in the polarity of the membrane ahead of the action potential. This change in polarity causes the voltage-gated sodium channels along this part of the membrane to open. Again, sodium ions rush in, and the action potential spreads to the adjacent part of the neuron. In this way, the action potential travels down the neuron like a wave. The efflux of potassium ions during the falling phase of the action potential restores the negative charge inside the neuron. Meanwhile, the sodium-potassium pump has been shuttling sodium ions out and potassium ions in, re-establishing the resting distribution of sodium and potassium ions.
Let's look at another action potential as it moves along the membrane. This time we will measure the voltage changes that occur in one spot along the membrane. A slight change in polarity causes the voltage-gated sodium channels to open. Sodium ions rush in, causing a reversal in membrane polarity. Sodium channels close and potassium channels open. As potassium ions rush out, the membrane returns to being negative on the inside. The sodium-potassium pump then restores the balance of ions present at resting potential.
So one reason why I wanted to show this was it's nice because it shows that the sodium-potassium pump still has a job and that it's continuing to run. Somebody had asked me that question. And you also saw that these sodium ions diffuse down the axon to help propagate and conduct the action potential. I have to do this over here. Okay, so now we're going to talk a little bit about glial cells. The glial cells support the neurons by nourishing them. They modulate the extracellular fluid that surrounds the neurons. But an important thing they do for our purposes is that they insulate the axons. And they do that by wrapping their whole cell body around the axon, forming something called myelin, which we'll talk about in the next couple slides. So in the central nervous system, or CNS, which is composed of the brain and the spinal cord, you have oligodendrocytes that are forming the myelin. While in the peripheral nervous system, these are the nerves that are outside of the CNS, Schwann cells are forming the myelin. Myelin is that cell wrapped around the axon, so it's many layers of cell membrane, which are very rich in lipid. And lipid does not conduct electricity well. So because they're poor conductors, these cells make very good insulators, and they don't let the electric current leak out of the cell. There are lots and lots of glia. They outnumber neurons 10 to 50-fold. So that's just to impress upon you that these cells have very important jobs in the nervous system. Now here's a picture of the myelin sheath. So here is the cell body and the axon, and you can see these cells wrapped around the axon forming the myelin. This is the peripheral nervous system because they're showing you these are Schwann cells. There are places where there is no myelin, These are called the nodes of Ranvier. The nodes of Ranvier contain the sodium-potassium ATPase and the voltage-gated sodium channels that are required to initiate an action potential. So these areas that are coated with myelin don't have these things and can't generate an action potential. The ion flow occurs only at these nodes during the action potential. And that means that the action potential will jump from node to node down the axon. And this allows conduction to occur quickly, even in the small axons that mammals like us use. So here's another picture of that blown up. These are the Schwann cells here, or oligodendrocytes in the central nervous system. Here's one of those nodes. You can see the voltage-gated sodium channels are clustered in the node and not present in the part that's coated with myelin. The sodium potassium ATPase is here as well. How do you think they stick in the node? They're anchored to cytoskeletal elements so they don't diffuse away. So they're held in these positions at the node. Having this kind of conduction, it's called saltatory conduction, makes neurotransmission faster because it's jumping from node to node. And it also saves energy. You only have this ion flow at the nodes, so you don't have to maintain this great expanse of membrane. Pumping ions back in and pumping them out to create the gradients takes a lot of energy. So this will be a nice approach to cost efficiency. Multiple sclerosis is a disease where people lose their myelin. It's probably an autoimmune disorder where the myelin gets degraded and lost, and they have a whole bunch of different neurologic symptoms, very diverse symptoms, because you rely on myelin for many neurological tasks to work smoothly. So this disease emphasizes that the myelin does a very important job in your nervous system. Today we're going to spend a fair amount of time talking about chemical synapses. In most cases, when a neuron passes a signal to another neuron, it's not passing electrical current or action potentials. What happens is that in most synapses, chemical neurotransmitters are released and pass the action potential onto the postsynaptic neuron across a narrow gap, which you'll see on the next slide. The neurotransmitter receptors in the postsynaptic cell then convert the chemical signal to an electrical signal. So you have an electrical signal traveling down the presynaptic neuron. It gets to the synaptic terminal and it causes the release of a chemical. So you get electrical signal to chemical signal. The postsynaptic neuron takes that chemical signal and converts it to an electrical signal, which could be an action potential that goes down the next axon. Presynaptic neuron. So I just used that term. Which one is the presynaptic neuron? It's the one that packages the neurotransmitter into vesicles. They get released into the synaptic cleft. So there's a very small space between the presynaptic and postsynaptic neurons. That's about 50 nanometers wide. A virus is about 100 nanometers in diameter, so that's a pretty small cleft. These vesicles holding the neurotransmitter are called synaptic vesicles. When the action potential comes down the axon of the presynaptic cell, when it gets to the synaptic terminals, it activates voltage-gated calcium channels in the membrane. And this lets calcium rush into the synaptic terminal because calcium is higher in the extracellular space than in the cytosol. This calcium influx will cause the synaptic vesicles to fuse with the plasma membrane. This is sort of similar to what we saw in the cortical reaction, and actually the acrosomal reaction is also triggered by calcium, although we didn't talk about that. There are proteins that modulate membrane fusion that are sensitive to calcium. When calcium comes in, it allows the synaptic vesicles to fuse with the plasma membrane. So here's a picture of what a synapse looks like from the book. We have the presynaptic cell, and the synaptic terminals are on the postsynaptic cell. So here's the presynaptic axon. The action potential will travel down here. When this membrane gets depolarized, it will activate the voltage-gated calcium channels. And calcium will go from high concentration to low concentration, and this will cause the synaptic vesicles to fuse with the plasma membrane because it activates a calcium-sensitive protein. When these vesicles fuse with the plasma membrane, they dump their contents into the synaptic cleft. The neurotransmitter will bind to receptors that are on the postsynaptic cell, and in this case, we're looking at an ionotropic receptor that is actually an ion channel itself. The neurotransmitter binds and opens that channel. We'll talk about that a little bit more in a minute. Okay, at the synaptic terminal, the rate of exocytosis and endocytosis are matched. What do you think? All right, well, I'm afraid this wasn't a good thing. The answer is true. Okay? Think about why. What happens when there's a bunch of exocytosis here and these vesicles are fusing with the plasma membrane? Does the plasma membrane get bigger or smaller? You're adding new membrane. It's growing, right? If you fuse a bunch of vesicles with a membrane, it increases the surface area of the membrane. It's going to get bigger. So if you don't want that membrane to get bigger, you have to take the membrane back in. So in general, in most cells at homeostasis, at equilibrium, exocytosis and endocytosis have to be pretty reasonably well matched. Otherwise, the volume of the surface area of the plasma membrane will change. It does change, but you don't want it to change by a ton. So the answer was true. We talked about the postsynaptic neuron just a second ago as being the one that has the neurotransmitter receptors, and I mentioned the term ionotropic receptor. So these are receptors, transmembrane proteins, that when they bind to their neurotransmitter ligand, they open. They are ligand-gated ion channels. So when the ligand binds, the channel opens. And these are in the membrane of the postsynaptic cell. You can also have metabotropic receptors, and these are a little bit different because the ion flow depends on an intermediate step. The channels, the receptors themselves are not ion channels. They work through an intermediary. So, for example, a G protein. When the metabotropic receptor, the neurotransmitter might bind, that might activate a G protein, and then the G protein would cause the opening of an ion channel. Ions moving across the plasma membrane of the postsynaptic cell are going to create changes in memory potential. These are called postsynaptic potentials, and these are graded potentials. So not like an action potential. You're going to get a change in the membrane potential that will degrade over distance from the source. And these are relatively small changes compared to what you see with an action potential. Now this is something I stole off the web. We have a top cell here and a bottom cell. Which one is the presynaptic neuron? The top or the bottom? Presynaptic. Bottom. How do you know that? Synaptic vesicles, right? So this is filled with little vesicles that are going to fuse with the plasma membrane when calcium enters from the extracellular space. What are these guys? They have lots of folds. You might call them cristae. Yeah, mitochondria. Why do you need a bunch of mitochondria around? Because making all these ion gradients costs a lot of energy. Okay, so there's some mitochondria there to help fuel this process. This is the postsynaptic neuron, and this dense stuff here, you don't need to remember this, is a postsynaptic density. And that is material that helps control the trafficking of the neurotransmitter receptors in the postsynaptic cell. What do you guys think this black stuff is over here? These are a bunch of neurons. So what's this black junk? Myelin! Yes, I showed it to you on an earlier slide. You can see the layers very nicely. So if this were the CNS, this would be an oligodendrocyte wrapped around the axon of a neuron. I like electron micrographs. I was at a transmission electron micrograph. So this neurotransmitter binding to its receptor could either hyperpolarize or depolarize, depending on which receptor it binds. ion channels that increase permeability to both sodium and potassium at the same time will actually depolarize the cell. Why is this? Well, when the neuron is at rest, the membrane is selectively permeable to potassium. So the membrane potential was closer to the equilibrium potential for potassium, which was minus 90. So our cells are pretty negative because only potassium could move, so we're close to minus 90. But now you're going to let sodium move as well. So yeah, okay, potassium's moving, but sodium can move now too. So now you're going to move up towards plus 62. So even though both sodium and potassium are moving, you will move more positive from minus 60 to minus 80. So allowing both sodium and potassium in together will depolarize. We'll call this an excitatory postsynaptic potential because it's moving the cell closer to the threshold. At rest, it's down here at minus 70. It has to get up to minus 55 to fire an action potential. So an EPSP moves it from minus 70 towards minus 55. On the other hand, if the ion channel is permeable to potassium selectively or to chloride, then it's going to help keep the cell below minus 55, and it's going to cause an inhibitory postsynaptic potential. So if you just increase permeability to potassium, like we talked about last time, then the membrane potential will go down towards minus 90. The cell will be hyperpolarized and farther away from the threshold for an action potential. See how you do with this? Botox, that people use to get rid of wrinkles, actually inhibits the release of the neurotransmitter acetylcholine. Botox could work by any of these mechanisms except. So we're looking for the one that couldn't be the mechanism for Botox to cause less release of acetylcholine. Okay? So I think part of the reason why we have this is because it's hard to answer questions that say except, and this one is actually kind of a double negative, which makes it a little bit tricky, but let's walk through this. So we know that Botox inhibits acetylcholine release. Which of these mechanisms would inhibit acetylcholine release? If you walk down the problem. Inhibiting voltage-gated calcium channels in a presynaptic neuron. You didn't get calcium into the synaptic terminal, no acetylcholine release. Check, that one's right. So it's not the correct answer, because it could be a mechanism for this. Inhibiting voltage-gated sodium channels in the presynaptic neuron. These channels are required to propagate the action potential. So if there's no action potential in the presynaptic neuron, no acetylcholine release. So this one could work. Check. What about this one? Binding to acetylcholine receptors. Where are acetylcholine receptors? Postsynaptic cell. Are they going to interfere with release? No. So this is the correct answer to the question because it could not explain. It is not a way to block acetylcholine release. Blocking membrane fusion proteins is how Botox actually works. So botulinum toxin inactivates a protein that's required for fusion of the synaptic vesicles with the membrane. So these excitatory postsynaptic potentials and inhibitory postsynaptic potentials are coming from lots of presynaptic neurons. Here's the cell body of a postsynaptic neuron. And you can see there's many synaptic terminals. Lots of presynaptic cells are telling it what to do. All these cells are telling it what to do, and it has to decide action potential, no action potential. It needs to integrate the information from all of these inputs to decide whether, or to, it will determine whether the cell has an action potential or not. And what determines that is whether the threshold of minus 55 for the voltage-gated sodium channels is reached at the axon hillock. So the axon hillock is where these voltage-gated sodium channels are dense. So if the potential at the axon hillock reaches minus 55, then an action potential will fire. Temporal summation. That's one way that this input can be integrated. So here we have a postsynaptic neuron. It's got a couple of presynaptic neurons forming synapses with it. First, we're going to look at this excitatory synapse here. And what happened was there was one EPSP, and then the potential went back to resting. And there was a second EPSP, and the potential went back to resting. This was not enough to depolarize the cell to the threshold, so no action potential was fired. In this neuron, over here, we're seeing temporal summation. So now we have two action potentials coming down this presynaptic neuron in rapid succession. So before the membrane potential change from the first one is decayed, you get a second one. And so these will sum. They will add together. And in this case, they brought the neuron to threshold and an action potential fired. So here you can see the action potential is originating at the axon hillock where the channels are concentrated and moving down the axon. Temporal refers to things that happen in time. So temporal summation, that means that two signals come close together, and so their effects are additive, close together in time. This is another presentation of the same idea. So here we have EPSPs arriving at the postsynaptic cell, and they're causing graded potentials, small depolarizations. And here we have 200 presynaptic action potentials per second. By the time the second one comes, the first one is pretty much decayed, so there's not much that's being added here. The green is showing you the summation, little summation at this frequency. But then we're going to double the frequency, so now the action potentials are coming twice as fast. And the second one comes before the first one has returned back to rest. The potential has returned back to rest. So you get some summing. If you double the frequency again, then these guys will add together even more, and eventually you can work towards that action potential threshold of minus 55. And you can see that these are millivolts, so we're talking about changes that are much smaller than you would see with an action potential, because we're just moving from minus 70 or so up to minus 55. Now that was temporal summation. You can also have spatial summation, and here we have two different presynaptic neurons that are going to produce EPSPs, and they're both firing at the same time. So this is spatial summation, where two different positions in space, two different neurons are providing signals, and these are getting summed in the cell body. So E1 plus E2 is enough to get to threshold, and you see an action potential originate at the axon hillock. This can also, the summation can also occur if you have an inhibitory presynaptic neuron in the, if you have an inhibitory signal and an excitatory signal. If it is the excitatory alone, it will depolarize a little bit. The inhibitory alone will hyperpolarize a little bit. And the two together will actually end up kind of canceling each other out, and there won't be much change. Let's see if you get this. Let's try a quicker question. This is actually an old exam question. Okay, I'm going to encourage you guys to explain your answer to your neighbor, because that helped a lot in section A, and then change your vote if you need to. vote again, if you haven't. Everybody get their new vote in? And that is much better. Yes? So it proves when you talk to your neighbors that studying together might not be a bad idea, reinforcing that idea. So you're having 6 that are minus 0.5 and 2 that are plus 0.5. So when you sum those together, you get a total of minus 2. So you go from minus 70 to minus 72. Somebody got a question? No? A sad question? All right, try this one. Okay, click in if you have not. Okay, this is a bit of a problem, so let's try this one. A neurotransmitter that produces an inhibitory postsynaptic potential through it acting on an ionotropic receptor. So what's an ionotropic receptor? Ligand-gated channel, right? It's one that binds the neurotransmitter and then opens. So I've told you the answer if you know what this means, right? So only one of these is a ligand-gated channel, all right? That's one way to get to the answer quickly. You also know that if we're going to have an inhibitory postsynaptic potential, then you either have to selectively let in potassium or let in chloride. So you know this answer is wrong. Leak channels are not really gated. For our purposes, they just are always open. Voltage-gated channels, remember, there's a synaptic cleft. The voltage doesn't jump across that cleft, so the answer is definitely D. So after that, let's try another one. Okay, you guys are doing well on this one. That's good. All right. Very good. So remember, this time we have an excitatory EPSP, and you can do that by letting in both sodium and potassium at the same time. I put in this clicker question to make sure that you guys got that point, that these ligand-gated channels will let in both sodium and potassium at the same time, and it still depolarizes. Okay, the properties of the receptor for the neurotransmitter are what's going to determine if you have an excitatory or inhibitory postsynaptic potential. And acetylcholine is a great example of this concept. Acetylcholine is a neurotransmitter. At the neuromuscular junction, where neurons and muscles have a junction, there are ionotropic nicotinic receptors for acetylcholine. So they're ionotropic, so they themselves are ion channels, and we call them nicotinic because they bind to nicotine. These are ligand-gated ion channels. The ligand is acetylcholine, and they're permeable to both sodium and potassium, so they're going to produce EPSPs, excitatory postsynaptic potentials. In heart muscle, however, there are metabotropic muscarinic receptors, and these guys use a G protein as an intermediary to open potassium selective channels. So if you do that, you're going to produce an inhibitory postsynaptic potential. So depending on what kind of receptor acetylcholine is binding to, it can produce an EPSP or an IPSP. It is the receptor that determines whether it's going to depolarize or hyperpolarize. And here's an example of that. So when you activate nicotinic receptors, you see you get a membrane depolarization. When you activate muscarinic receptors, you get hyperpolarization. And remember that these are graded potentials. They're not action potentials. They're not self-propagating. These graded potentials degrade from their source. Another clue is you can look at the magnitude of the change in voltage here. It's nothing like an action potential. Okay, another practice. Okay. Not a great sign, but not terrible either. So one of the reasons why I'm giving you so many questions today is because a lot of you have said you have problems with these synthesis application questions. So I've given you a lot of those today. And it's not just about knowing what the right answer is, it's knowing about how to get to the right answer. So the explanation is as important as the right answer for these guys. So we had a toxin, curare, that's used for poisoning blowgun darts, and it causes muscle relaxation. So your goal here is to figure out which of these could relax the muscle. You prevent closure of nicotinic acetylcholine receptors. I just told you that those produce EPSPs by letting in both sodium and potassium. So if you stop them from closing, you're going to make the muscle contract even more. So A is gone. Blocking acetylcholine degradation. If you leave acetylcholine in the synaptic cleft for a long time, it's going to keep stimulating the postsynaptic neuron. So that's bad. That'll cause muscle contraction. Not right. Stimulate calcium entry through voltage-gated calcium channels. I don't think many of you guys like that, which is good. Because if you let calcium in, you're going to cause the synaptic vesicles to fuse and release more neurotransmitters. That's going to cause contraction too. So the right answer is this one. Bind to the nicotinic acetylcholine receptors with high affinity. And this is a really important concept that I think when you're new to biology might be a little tricky, is that curare works as a competitive inhibitor. It binds to the same place as acetylcholine does, but it doesn't open the channel. And this is the way a lot of inhibitors work in biology. They bind to the same spot as the natural ligand, but they don't cause a natural effect. So the correct answer is D. I don't want to say a lot about this. Amino acids can be neurotransmitters. You can read more in your book. And several neurotransmitters are derived from amino acids. You can read more in your book if you're interested. These things are interesting. So I want to talk about some other things. Neurotransmitters must be removed from the synaptic cleft. Why? You guys did a great job on this one. The answer is definitely B. That was good work. If you leave the neurotransmitter lying around, you're going to keep stimulating that postsynaptic neuron. When you turn a signal on, you immediately start turning it off. That's how biology works. So how do we turn off the signal from neurotransmitters? We have to do that to have temporal and spatial precision of our signaling. One way is you can retake up these neurotransmitters into the presynaptic neuron. So they take the neurotransmitters back, repackage them in synaptic vesicles again, and can re-release them. And that's going to be recycling, is a bioenergetically favorable way to approach this problem. Another one is you can degrade the neurotransmitter that's in the synapse. And an enzyme, ACE here, that does this is acetylcholinesterase. It is an enzyme that degrades acetylcholine. So now I have another problem for you to try. And most of you guys saw that this is really exactly the same question I just asked you. Okay, so the answer is D. In this case, I made it a little more complicated, told you a story. Now we're inhibiting the enzyme that degrades acetylcholine. So we're making more acetylcholine in the synaptic cleft. It's the exact same question I just asked you, but 20% fewer of you got it right. Okay, it is promote prolonged stimulation of the postsynaptic cell. Okay, slight twist. So I know you guys can do this stuff. Draw yourself pictures. So you got the other one right. I will post that because I've got another thing to cover before we're done. It is a very helpful video though, so I would encourage you to watch it. Monitoring brain activity through bioenergetic demand. So I think this is a nice synthesis of a lot of the concepts we talked about. There's two ways you can do this. One is FDG PET. This stands for fluorodeoxyglucose positron emission tomography. Quite a mouthful. In this technique, you give the patient radioactive glucose, and you can use this to monitor glucose uptake in different cells in the body. Your brain uses a lot of glucose, so you can use it to monitor brain activity. And you can combine it with a CT scan, which is like a three-dimensional X-ray. fMRI stands for functional magnetic resonance imaging. And in this case, you're measuring changes in blood flow. So the blood is, of course, delivering glucose to the neurons as well as oxygen. And in this case, you don't need any label or contrast. MRI looks at water molecules, and you can look at the change in blood flow without any contrast agent involved. So the take-home message here is that thinking requires a lot of energy. Neurons are very metabolically active, right? They have to pump all these ions in and out and reestablish them when the channel's open. They have to make the neurotransmitters. Endocytosis and excitatosis take lots of energy. So neurons are very metabolically active cells. All that pumping requires lots of energy. So here's an example of functional MRI imaging. This is from your book. You can see that when somebody's listening to happy music, certain parts of their brain are active. When they listen to sad music, different parts are active. So we're getting to the point where we can almost read somebody's mind by looking at their brain activity. Studies have been able to guess what kind of a picture somebody is looking at. This is a PET scan. You can do the same sort of thing. You see different areas of your brain are active when you're hearing words, seeing words, speaking words, generating words. You can follow this by looking at glucose uptake by those cells. This is a really cool story. So here, there was a 23-year-old woman who was in an auto accident and sustained severe injuries that caused her to go into a coma. And she was in a vegetative state for about 5 months. She had normal sleep-wake cycles, but was not conscious, was not responsive. And she was involved in this study. So they took some control, normal individuals, and told them to think about playing tennis. And this part of their brain lit up. Then they told them, imagine you're taking a tour of your house, starting at the front door, going each room. And these areas of their brains became active. They asked this lady in the vegetative state the same question. The same area of her brain became active. When they asked her to take a tour of her house in her brain, the same areas became active. So this suggests that on some level, she was actively conscious, even though she was in a vegetative state. This is even cooler. So then they told her that when you think about tennis, that's going to mean yes. And when you think about touring your house, that's going to mean no. And they asked her a series of questions. Was your father's name Andrew? No. Was your father's name Thomas? Yes. Do you have a brother? Yes. Do you have a sister? No. And so they were actually able to communicate with this woman, and you can imagine that has profound ethical implications for how we handle people in this situation. This is very cool. So here, they did the same thing. They had people think about different things, right? And when they think about tennis, now they move their palm paddle up, and when they think about touring their house, the palm paddle goes down. They were able to use software to have two people play Pong with each other in real time by thinking about things. So you can imagine I could think, lights off, and the lights go off, right? Start car, car starts. Very cool possibilities for the future. And this was kind of complicated, but most people can figure out how to activate different areas of their brain after very little training. And to conclude, we use PET a lot in my field to look at cancer. So this person has disseminated melanoma. All these black spots are taking up lots of glucose because they're cancer cells dividing rapidly. This person was given a new therapy for melanoma, and you can see that that disappeared, but their brain is still very dark. Brains take up lots of glucose. So that's the take-home message. Come ask me questions. I'll see you guys Friday.